Hello, welcome everybody. Thank you so much for joining us today. I'm Vicky from the PTI and I'm delighted to welcome you all to our Enrich Maths CPD course today. I'm pleased now to hand over to Charlie and Alison. Thanks for joining and I hope you enjoy the course today.
Thank you very much, Vicky. Just a little bit then about what Charlie and I plan to do over the next hour and a half or so. We're going to go through a couple of tasks with you that hopefully you have seen before because they were the suggested pre-session tasks. But don't worry if you've only had a chance to look at them and you've not had a chance to look in detail, because we're going to talk quite a bit about the way that you might use the tasks in the classroom and the pedagogy and so on. And then we've got a couple more favourite tasks to share with you. And along the way, we're going to be talking generally about how to make geometrical reasoning a sort of enriched and connected and engaged topic for students. So to kick off, I'm just going to share my screen with you and show you our first task of the afternoon, which is Polygon Rings. And so just pop in the chat whether you did have a chance to look, if any of you did have a chance to look at this problem before today. If you are seeing it for the first time because you didn't get a chance to look at it, I'm going to put the link directly to the problem in the chat so that if at any point you want to just click on it and have a quick look in more detail, you know where to find it. Excellent. Some of you have had a chance to have a brief look at it. Lovely. Okay, well, this is how the problem starts off for the student view of it. So here is a pattern made of regular pentagons, and then there are 5 regular pentagons put together. And the first problem that students are invited to continue is whether they think continuing the pattern would form a complete loop, which we're going to call a polygon ring, or whether the pentagons won't fit exactly together and they will overlap. And one way that you can explore this is by using the interactive environment that appears in the problem. So I can click on the pentagon and then I can click 2 points. It uses Geogebra and that specifies the pentagon. And then I can draw my next one on by clicking 2 points in the pentagon and continuing to go around. So I can make exactly the same picture that we had in the picture at the top of the screen. So you might like to be thinking about what your answer to this question would be, whether it would form a complete loop or whether the pentagons would overlap. But I want to say a little bit about what the motivation for using this problem in the classroom might be. So one of the things that we have to teach is angles, and one aspect of angles is for students to know about the interior and exterior angles of polygons, and particularly how to find the angles in regular polygons. So when Charlie and I were discussing this, we thought that this might be a nice task to use because it could either be used at the beginning of a topic on angles as a motivation for students needing to know the formula, needing to know how to work these things out, or it could be used as a consolidation task. Once students have met the formula, then they can apply the formula in order to work on the ideas in this task. So what I'm going to do is I'm going to hand over to Charlie, and Charlie, you're going to explain a little bit about how you might derive the interior angles. So if I stop sharing.
Okay, thank you, Alison, and hello everybody. So I'm going to share my screen. Okay, so one of the messages I think that Alison are quite keen for students to take away with them is that it is possible to derive some of the formulas that they learn, but also that there isn't just one way of solving problems. And so when we were thinking about the formula for the angles of regular polygons, we realized that we've got 3 ways of deriving this that we quite like. So you may all be very familiar with all three, but we just thought we might rehearse them just in case you perhaps know two rather than three of them, or just to look at whether how your explanations differ from ours. So I'm going to just draw an irregular pentagon to start with. 1, 2, 3, 4, 5. And one way in which I can work out what the angles of a regular pentagon are going to be is to, first of all, start by working out the sum of the angles of a pentagon. So I'm going to start by choosing one of the vertices and draw lines to the vertices which are not adjacent to it. So I can draw 2 lines there. And what this does is splits my pentagon up into 3 triangles. And I know that the angles in a triangle add up to 180 degrees. So those 3 angles add up to 180 degrees. These 3 triangles, these 3 blue angles, green angles add up to 180 degrees. I made the same mistake this morning when I rehearsed this with Alison. And then the 3 angles, which I've marked in purple, add up to 180 degrees. And what we find is that all those angles added together make up the angles of the pentagon. And so I've got 3 lots of 180 degrees. Is what the sum of the angles of my pentagon come up to. And if the polygon was a regular pentagon, I would then divide the sum by 5 to work out what each angle comes to. And so this is for a 5-sided polygon. If I had a 6-sided polygon, then I would have drawn 3 lines rather than 2 lines. I would have split the hexagon into 4 triangles. So I would have had 4 lots of 180 degrees. And because I'm interested in the angles of a regular hexagon, I would have divided by 6 if I wanted to work out what each angle came to. And if I had an n-sided polygon, then I'm going to have n-2 triangles. So when I split the polygon up, I'm going to have n-2 triangles, and each one gives me 180 degrees, and I would end up dividing by n if I wanted to work out what each angle would be in a regular n-sided polygon. So that's one way in which I can derive the formula. So let's try and remember it's 180 n-2 divided by n, but I have a different way of deriving the formula.
So what I like about what you just did there, Charlie, is that you showed the example of 5, and then you led us on to think about what would happen if we went up to 6. And then I can imagine in the classroom, I might want to do a couple more numerical examples first, and maybe skip and say, what can you describe what would happen with a 10-sided shape? What would happen with a 20-sided shape? And then move on to the nth case. So it's like this idea of a generic example where we can use the numerical case as a way to get into that general thinking and then move to the algebra when we're ready for it.
Yes. I went to the general case much faster than we would do with a class of students. And I'm demonstrating here and not giving anybody any work to do. And of course, in a class, we would split this up, break this up, and make sure that students had a chance to do some work on this. Okay, so here comes another way of thinking about this. I've got an irregular pentagon, and I choose a point anywhere inside my pentagon. It doesn't have to be near the center, but just to make it easier, I'm going to draw it reasonably close to the center. And I'm going to just draw lines from my point to each of the vertices. And this time I've split. I wonder whether I should have drawn this a bit bigger. Okay, no, I've split the pentagon into 5 triangles. And luckily I've got 5 colors, so that's good. So the green angles are going to add up to 180 degrees. The black angles are going to add up to 180 degrees. The red angles are going to add up to 180 degrees. The purple angles are going to add up to 180 degrees. And the blue angles are going to add up to 180 degrees. So I've got 5 lots of 180. But given that I'm only interested in the angles in my pentagon, I've got to take away these angles in the center that I'm not interested in, which come to 360 degrees, or 2 lots of 180. And so I end up with 3 lots of 180 degrees when I've got a 5-sided polygon. And just like before, if this was a regular polygon, each of the angles would be the same, so I'd have to divide by 5. And if I had a 6-sided polygon, I would have been able to split my hexagon into 6 triangles. I would have had 6 lots of 180 degrees minus the angles in the center. So I would have ended up with 6 180s minus 360 or minus 2 180s. And so I would have ended up with 4 lots of 180 degrees. And if all the angles were the same, then I'd divide by 6. And just like before, for an n-sided polygon, I would have n triangles, so it's 180 degrees times n, minus 2 lots of 180 degrees, all divided by n. And this here would give me n minus 2. I'll work backwards. N minus 2 lots of 180 degrees divided by n, which is what we got on the previous sheet as well. So a different way of getting exactly the same formula. One last way of thinking about it. Let's draw again an irregular pentagon. And let's imagine that this is a park, and we're going to walk around this park. So I'm going to start here, and I'm going to be facing in that direction, and I'm going to walk, 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 and then when I get to this point, I'm going to have to turn, and then walk, walk, walk along there, and when I get to this point, I'm going to have to turn. I'm going to walk along here, and when I get to this point, I'm going to have to turn. Walk along here, and then turn. Walk along here, and eventually, to get back to where I started, I'm going to have to turn. I'm going to demonstrate this with my pencil. Notice that the pencil is starting by pointing sort of in a northeasterly direction. And what I want you to notice is what happens to the pencil as we walk around the park. So we go to there, to that vertex and turn, walk along here 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 and turn. And if you've been focusing on the pencil, you'll have noticed the pencil has gone through a complete turn of 360 degrees. So we know that these black angles here, these exterior angles, add up to 360 degrees. But we also know that the exterior angle plus the interior angles add up to 180 degrees. So we have 5 180 degrees, but we're not interested in the whole red angle because we're not interested in the exterior angle. So we're going to subtract all the black angles, which came to 360 degrees because the pencil went through a complete turn. And 5 lots of 180 degrees minus 360 degrees is the same as 3 lots of 180 degrees. And just like before, if all the angles had been the same, we divide by 5. And we can generalize in the same way as we did before for a hexagon and for an n-sided polygon. I'm not going to go through that because I think it's fairly obvious what I would do. So I think this is going to be a useful tool, and being able to work out the angles on the polygons is going to be important for what comes next. And some of you, so Alison's showed us the polygon rings. Some of you may have ATM maths in your school, so you may introduce this task to students by showing what happens if we put some ATM maths in a ring. I'm going to just lift my visualizer in a second so that you can see what the whole ring might look like. And it does look like this might work, but it's not clear what's happening here. It's not clear whether, you know, I can cheat a bit and make it look right, or this suggests that we can get close to a complete ring, but I'm not convinced that there are no gaps or overlaps. And so Alison's going to talk a little bit about how we convince ourselves whether this is a polygon ring without gaps or not. So I'm going to stop sharing my screen and pass on to Alison.
Thank you, Charlie. So this is one of those steps that you have in geometrical reasoning that, whether we're exploring with the ATM maps or whether we're exploring with an interactivity on the computer, we might have a conjecture that you can put 10 of these pentagons round to form a ring, but the geometrical reasoning comes in when we're explaining why it forms a ring, and that's leading towards the steps of geometrical proof that we'll talk about a little bit later. So I'm just going to outline to you what you might do in order to convince yourself that this forms a ring. And there are several different ways of coming up with a convincing explanation for this. And this one that that Charlie and I were exploring when we were planning this, I rather like. So I'm going to continue these two lines, and I'm going to think about the angles that I've got in this triangle, this white triangle that I've just made. So I'm going to call this angle here angle X. And then I know some of the angles because using Charlie's method, I know that this angle here, the angle of a regular pentagon, is 108 degrees. And so this angle will also be 108 degrees. And so then, considering my straight lines, I can work out these two angles by doing 180 minus 108, which is 72 degrees. And so that's 72 and that's 72. So then I get an equation that X plus 72 plus 72 is going to make a triangle, so it's going to be 180 degrees. And so x is going to be 180 minus 2 lots of 72, which is 144. So x equals 36 degrees. And then in order to convince myself that this means I can form a polygon ring, I can think about what would happen if I continued round. And so at each of these, I would get my x degrees. So that means that when I've got 10 of them together, I'll have 10x, which will be 360 degrees. So I know that in Charlie's picture, where there was a little bit of a gap and it looked as if they might not quite fit, I can prove geometrically that actually they do fit, because I know that 36 divides exactly into 360. So that's with a pentagon. I think in order to get the most out of this task, then it's a nice example of a low threshold, high ceiling task, because as well as exploring with pentagons, we've got all of the other different shapes that we can explore with. And so I made the ring with pentagons. I could instead say, what happens if I try and make a ring with hexagons? And it may be that for some students, starting with a hexagon and exploring what happens might be more appealing. It might use more familiar angles. So you might like to think about how you could adapt the proof shown for the pentagon for the hexagon. So that's the low threshold angle of it. When thinking about the high ceiling angle of it, then thinking about how this problem can go beyond, and for a student who finds this first part fairly straightforward, how they might be able to explore in more detail, you could start to think about other shapes. And so here I made, where is it? I made a picture with octagon. And the interesting thing that I found with octagons is there's actually two different rings that you can make. So I've got this ring up in the left, top left, where I can put 4 octagons together to make a polygon ring. And there's a square shape in the middle. So you could take the time to prove what's going on there. But you can also fit together 8 octagons to make a polygon ring with a star shape in the middle. And to start thinking about how that's going to work and how to prove that that has fitted without any gaps, what I can do is I can do the same trick as before and do the continuation of 2 adjacent lines, but then instead of having a triangle to consider the angles in, I've got this sort of arrowhead shape here, and I can work out all 4 of those angles based on what I know about the octagon, in order to show that the middle angle is in fact a factor of 360 degrees, that it's going to divide exactly into 360 degrees. So I know that I will get back to where I started from. However, what I really like about this, and this is, I don't like spoiling things. I kind of want people to be able to go away and explore this for themselves if they haven't already, but this is just, it's too good not to spoil, which is something that came out of a workshop that Charlie and I did a while ago. And we set this as a task for teachers to have a go at. And one teacher said, well, I'm going to do 7s because nothing ever works with 7-sided shapes. And so she used the interactivity to put things together. And she ended up drawing that picture. And the reaction that she gave when she put the last one into place and it fit perfectly without any overlap and without any gap, there was so much joy in that. The surprise that something worked with a heptagon, which has this horrible, irrational angle that, you know, it goes on and it's rational, but it's a recurring decimal. It's not a nice angle at all. And yet she got that picture and she could then draw her extra lines on it and prove that 14 heptagons make a polygon ring. So that's really starting to get into the high ceiling of this task. So yeah, the motivation for doing this task is because we don't have to tell students that there is a formula for working out the interior angles of regular polygons. We can show them how to derive it. And I can never remember the formula. Whenever I have to use it, I always have to derive it. But because it is so quick to derive, it doesn't slow me down at all to do that. And also, they don't need to memorize that a hexagon is 120 degrees, a pentagon is 108 degrees, an octagon is 135 degrees for the interior angles, because they can use the formula to work them out. So it's moving away from this idea of maths as lots of methods to be memorized, and more about something that makes sense that you can then deduce new information from. And I think that's really exemplified quite well in the second task that we would like to share for you.
Alison,
yes, Charlie.
just before you get rid of this image, could you just draw in where your arrowhead would be?
Oh, yes, of course.
Just to show, for anyone who's wanting to work on this, presumably that angle at the bottom of that arrowhead is 1/14 of 360 degrees.
Yeah, so you can work out what that angle there is, because it's the 180 minus that, and that angle there is 360 minus that, and that one's the same by symmetry. And so with those three together, you can do a little bit of manipulation, and you should get 360 over 14 for that middle angle there.
Right, and so even though the numbers are a little bit awkward, it is that is the number that tells us that with 14 heptagons we're going to be able to draw it. So we're not going to go through the demonstration of this, but
yeah, we want to leave people something to have a go at after the webinar, don't we?
Yeah.
Okay, I'm going to hand back over to Charlie then, so that we can take a look at the second problem that you might have had a chance to look at before today. And we're going to talk about how we might use the cyclic quadrilaterals problem in the classroom. So Charlie, I think you've got some, did you get 9 pointed circles in the end for this?
I did. Okay, so let me share my screen.
And I'm going to put the link in the chat again, so if anybody wants to play along on their own screen, there is an interactive version of what Charlie's got printed out there, so that you can draw quadrilaterals on the screen instead. Okay,
so we're going to focus on cyclic quadrilaterals, and we're going to use a 9-dot circle because the angles that we're going to be using are very straightforward. So if I draw a triangle like this, or a triangle like this, because the 9 dots are equally spaced around the circle, this angle here will be 1/9 of a full turn. So that'll be 40 degrees. And this angle here, because it spans 2 dots, the space between 2 dots, it's going to be 80 degrees. And of course, I could have something larger. I could have that triangle, and so 3 spaces will be 120 degrees. So I'm going to be using that. So we've chosen a 9-dot circle because we don't want the arithmetic to get in the way of what the students are doing. We want the numbers to be as simple as possible. Okay, so we might ask students to draw a variety of quadrilaterals where the vertices are on the dots. So here we are, I could draw something like this. But of course, there are many more. I could have drawn something like that.
And I assume, Charlie, that if you're doing it in the classroom, you'd invite students to draw this with a pencil and a ruler rather than freehand with a Sharpie, right?
Absolutely, and the sheet has got sort of 6 circles, and I'd encourage them to draw 6 different quadrilaterals. So I'm just going to focus on one, and so once they've done this, I would ask them to split their quadrilateral into triangles by joining the center of the circle to each of the 4 vertices, and to then work out the angles of the quadrilaterals by first of all working out the angles of their triangles. So here we go. We had a 40 degrees here in the center. So these 2 angles must add up to 140 because all of them add up to 180. And because the triangle is isosceles, we've got a radius here and a radius here, they're identical. So we've got 70 degrees in each. Whereas this angle here was an 80-degree angle, 2 lots of 40. So these angles add up to 100 degrees, but because it's isosceles again, they're each 50. Here we've got 120 degrees, which leaves only 60 degrees. And because it's isosceles, we get 30 degrees for each. And this is identical to that triangle. So again, that's going to be 30 degrees and that's going to be 30 degrees. So like Alison says, we would ask lots of students to do this, lots of different quadrilaterals, and then we'd be asking them to give us the angles of the original quadrilateral. And one of the things I do is I ask them to give me the angles in order. So I don't mind where they start. I don't mind whether they go clockwise or anti-clockwise, but once they've started going in one direction, I want them to carry on in the same direction. So for example, if this is vertex A and that's B, then that would be C and that would be D. And on the board, I might start making a table of values with the values for A, B, C, and D. And in my case, angle A is 100 degrees, angle B is 120 degrees, angle C is 80, and angle D is 60. And we would gather information from all our students and ask them to tell us what they notice. One thing that they'll notice is that there are multiples of 10. Another thing they might notice is there are multiples of 20. So this is quite nice because as a teacher, as you wander around the class and want to check that students are getting this right, it's really easy to check that their angles are all multiples of 20. But the other thing they might notice, angles A and C always add up to 180 degrees. And because they add up to 180, the other pair must add up to 180. So you can imagine a table of values here, and this happens throughout. A question that students sometimes, you might ask, well, does this always happen? Does it happen even when my quadrilateral is drawn in such a way that the center of the circle appears outside of the quadrilateral? So this seems slightly trickier.
While you're drawing the lines on there, Charlie, it's that second example without the dot in the middle is a nice way of using this as a low threshold, high ceiling task, because you could have some students who only work on the examples where the dot is in the middle, but then some students, you might want them to have a go at working out how to do this without giving them a method for working it out. Can they figure out how to work out the angles in a case like this?
Yes, initially, I always ask them to draw at least 4 or 5 different quadrilaterals with the center inside, and then give them the opportunity of drawing 1 or 2 with the center outside that we come to perhaps later if it seems appropriate. So I may not go through the whole method, but you can see that these angles here are going to be 70 degrees each for the same reason as we've already talked about. This is 80 degrees here, so there's going to be a 50 here and a 50 there. But I don't want this little bit here. So I need to start thinking about this triangle here, which is which spans 1, 2, 3, 4 circles. So this angle here is 160 degrees. So these little angles here will be 10 degrees each because it's isosceles. And so the angle that I'm interested here is going to be 50 degrees minus the 10. So that angle there is going to be 40 degrees. And this angle here is going to be 70 degrees. Let me just check. Yes, 70 degrees minus 10 degrees. So the angle that I'm interested in here is going to be 60 degrees. And once all the angles have been worked out, students will discover that actually the 2 opposite angles do again add up to 180 degrees.
Yeah, and I think that's where your ABCD labeling comes in really useful here, because when we talk about opposite angles, I can imagine some students having the misconception that what you're about to label A and D are opposite each other because they're on like opposite sides of the circle. But of course, when we talk about opposite angles in a cyclic quadrilateral, we mean A and C and B and D. So when we're using mathematical terms like opposite that have a particular mathematical meaning, making sure that we're aware of students not getting confused with a more colloquial meaning and having that precision there is really important.
Now, it's all fine that we've discovered that in the examples that we've done, the opposite angles of the cyclic quadrilaterals on a 9-dot circle add up to 180 degrees. But so one question that Alison and I might ask the students is, does this convince you that it always works? And that you'd hope that students might display a bit of skepticism. So they might suggest that, well, it only works because there are 9 dots. And so at Enrich, we've got some 10-dot circles, we've got some 12-dot circles, we've got some 15-dot circles, we've got some 18-dot circles. And so what we've done in the past is given out maybe to different groups, different dot circles, and said, okay, let's just see, can each group work on different cyclic quadrilaterals on their circles and see what happens, give them plenty of time. Basically, they're replicating the kind of method that I demonstrated a minute ago. And surprise, surprise, or they all come back and confirm that the opposite angles did indeed add up to 180 degrees. And Alison and I might ask, well, does that convince you that this always works? And again, you hope that at least some students will be a bit skeptical and might say, wait a minute, you know, 18 dot, 15 dot, 12 dot, 10 dot, these are all factors of 360 degrees. Why didn't you give me a 7-dot circle or an 11-dot circle or maybe it only works when the number of dots fits nicely into 360 degrees. So the response might be, okay, we really do want to prove that this always works. So I drew a circle in advance in Blue Peter style. And I'm going to just choose 4 dots at random. So a couple of dots and a couple more. I can never make this look completely random, unfortunately.
Yeah, it's almost impossible not to draw something that ends up looking like a trapezium or a rectangle or something.
Okay, I'm going to come to... And the question is, do the opposite angles of this cyclic quadrilateral add up to 180 degrees? And there is a very nice proof, but students working on this may find it a little bit difficult without sort of nudging them in the right direction. So I'm going to help you as well, and I'm going to give you a little bit of time to think about this. And our nudge is this. We've been working on all the examples so far by splitting our cyclic quadrilateral into 4 triangles, 4 isosceles triangles. And let me get my pens ready. And in this isosceles triangle here, these 2 angles are the same. In this isosceles triangle here, these 2 angles will be the same. In this isosceles triangle, these 2 angles will be the same. Those purple look a little bit like the blacks, so I'm going to just put circles around them to make sure they look different. And in this triangle, these 2 angles will be the same. And our question to you is, how can you use what you see on the screen at present to convince yourself that the opposite angles of this cyclic quadrilateral are up to 180 degrees? We'll give you just a little bit of time to think about it, and then perhaps in 30 seconds, a minute, you'd like to post something in the chat.
Yeah, while people are thinking about that, it's interesting to note that with the specific examples on the 9-point circle, 12-point circle, 18-point circle, and so on, where you've put the crosses in this diagram, we were putting actual numbers, but now we're less interested in what the number is, and we're more interested in where there are 2 angles that are the same as each other. And so we've split the circle, the cyclic quadrilateral, into 4 triangles, so you end up with 8 angles, but they're 4 pairs of angles. And I think understanding that is really key to understanding this proof. So does anyone have an argument, a convincing argument to put in the chat to show how this diagram means that we have opposite angles adding up to 180 degrees? So Susan started us off by saying all of the marked angles add up to 360 degrees. So the 2 greens, the 2 blacks, the 2 reds, and the 2 purples all together make 360. I agree with that because it's a quadrilateral, and I know that quadrilaterals add up to 360 degrees. And Eleanor says a pair of opposite angles includes 1 of each colour. And yes, Sally, I think it is much easier for us to use letters rather than colours when we're, as maths teachers, referring to this. For some students, using colours rather than letters can offer a useful piece of scaffolding. But yes, my preference would be to use letters for this. And so what Charlie's showing on the screen now is almost a proof without words. It's got some numbers in it, but all 8 of them add up to 360. But each of the opposite pairs has 1 of each colour in it. And so that means that the opposite pairs add up to half of 360. So there's our proof that the opposite angles add up to 180.
And people after today might want to adapt that for a quadrilateral where the center of the quadrilateral, where the center of the circle is outside their quadrilateral. So there'll be some pluses, just like we got there, but there'll be some minuses as well. So slightly more complicated, but just like Alison said, it is similar, it mirrors what we've done with numbers.
Yeah, and so it's exactly the same sort of journey that we're taking with the interior angles proof, beginning with a concrete example using numbers that students can anchor their understanding on, and then moving to the generalization, but that students can always refer back to the comforting case with actual numbers to help them to understand, rather than just diving straight in with a formula and not really knowing where the formula comes from.
And I think, Alison,
okay,
I think both you and I often forget some of the formulas that are used if we don't use them very often. Yeah. And it doesn't worry us, because both of us know that we can deduce and derive these formulas fairly quickly. And we'd hope our students start feeling confident they can do this.
And I think it's easier to remember things as well if you sort of, if you've got more of a handle on where it comes from, then you're more likely to be able to remember it anyway. And so it's kind of like a double whammy. You find it easier to remember, but also, even if you forget it, you know you can get it back again. Okay, I'm going to take over sharing now so that I can
check, Alison. Yep. Were you going to ask me to draw some rectangles on some
I was going to show a couple of things on the Cyclic Quadrilaterals page on the site to show that little bit.
Okay.
So if I share the problem on the site, so everything that we've just gone through is all here within the problem, and there are interactive versions for the different circles. You can also, and there are links to them, you can print out the 9-dot circle, the 10-dot circle, and so on from this page. And there are links in the teacher's resources to other tasks for other circle theorems. So one question that I quite like to ask is, using a 12-point circle, which is this one just here, how many different rectangles can you find? And so if I join that point to that point to that point, and like that, that looks like it's a rectangle, but can I convince myself that it's definitely a rectangle? And of course, the thinking that you do in order to convince yourself of that leads to the fact that when you're showing that that's a right angle, it's dependent on this being a diameter. So if I try to do the same thing on the 15-dot circle, I find that I don't have a diameter because I've got an odd number of points, and so I can't get a rectangle. So you can get the result that the angle in a semicircle is 90 degrees by exploring rectangles on a grid. And as with all problems on the Enrich website, in the teacher's resources, you've got some discussion on the sort of things that Charlie and I have just been talking about. And you've got an image to suggest how the proof might work. But then in the possible support and the possible extension, there are links to other problems that you can use to think about exploring the circle theorems. I'd be interested if people could just pop in the chat. When do you usually do circle theorems in the curriculum? So what year group would you normally introduce cyclic quadrilaterals to? Okay, so people are seeing it as a Key Stage 4 topic for the most part. A couple of people saying Year 9. Yeah, I'm not surprised by that. It feels like it is very much a Key Stage 4 topic. And yet a lot of the preliminary stuff that Charlie and I have just gone through would actually make really good consolidation work as part of a Year 8 angle topic. And you can do you might not be able to do the last bit of generalization with most Year 8s, but yeah, you can certainly do quite a bit of what we've done in Key Stage 3 and prepare the ground for this geometrical reasoning and then applying the circle theorems in Key Stage 4. Talking about proof then, what I want to do is I want to switch to the visualizer for a bit to show you another problem which really gets into this idea of geometrical proof. And so I'm going to present it first of all in what I think is quite an unfriendly way. So let me read this out for you and give you a moment to think about it. So ABCD is a square, M is the midpoint of AB, E is the intersection of AC and DM, F is the intersection of BD and CM, G is the intersection of AC and BD. What proportion of the area ABCD is the area of the kite EGFM? So if you were presented with this problem to solve, what would be the first thing that you would do? Suggestions in the chat. Yeah, exactly, Ruth. I hope that's everybody's response. I don't think it is possible to solve this problem without drawing a diagram. And while Charlie was drawing things out before, one of the things that we do when we're working geometrically is we try and draw nice big clear diagrams and label the diagrams and start introducing students to the conventions that we use when we're working geometrically. So the fact that you can determine a line by talking about the two endpoints of it, the fact that we usually use capital letters to mark points, that we can talk about the intersections between lines, and also thinking about, you know, the difference between an accurate diagram and a sketch in geometry. But I think perhaps you will feel happier about this problem if instead I give you that picture. So that picture represents pretty much everything that was said in words, but is immediately a bit more visually appealing. So I'm going to give you just a couple of minutes to have a look at that shaded area there. And I don't think this is the sort of problem that you can just solve in a couple of minutes. I certainly didn't the first time I saw it. But I'd like you to think about what you might do as your first steps for solving this problem once you've got a nice clear diagram and you know what it is that you're trying to work out. So yes, it is exactly. A picture's worth 1,000 words. If you're ever asked to write a 5,000 word essay, though, most people don't like it if you just submit 5 pictures instead. But yeah, so have a little think about how you might approach and what your first steps would be the problem. And then we'll talk about what might happen in the classroom with this. Okay, what I'm going to show you now is I'm going to show you a slightly different set of diagrams. So it's the same problem. I wonder if anyone can spot the difference between the first picture I showed you and then this second set of pictures that I've showed you. Might be a little bit difficult to see because of the resolution of the visualizer. The main difference between the first picture and the second set of pictures is I drew these ones on squared paper. And I think it's amazing the difference that it makes to thinking about a geometrical problem if you're presented with it on squared paper or dotty paper as opposed to plain paper. Because I think it's I'm not necessarily saying one is better than the other. I think it leads your thinking down different ways. So if anyone has got any suggestions of the sort of geometrical techniques that you think might be useful in approaching this problem, just drop in the chat now and any suggestions of which areas of geometry or which techniques might be useful in order to start figuring out what that blue shaded area is as a proportion of the square. Okay, so I could work out as many different areas of triangles as possible. Now, at the moment, this is a question about proportion rather than actual area. So I don't actually know any lengths at the moment. So using the second one with the squared paper, I can start imposing lengths on it because I've got a square grid, and so I can start calculating in square units. But on the first one, it might be a little bit harder to start working out actual areas straight away. So the nice thing about on the square grid is you can almost do it by counting squares. You can certainly start to think about how to split the triangle up into things that you can calculate. And then that leads us to one of the top tips that I always give students when working on geometry, which is, are there any extra lines that you can draw that will make it easier to work out? And so, yes, starting to see where there are bits of area that you can divide up and proportions of the original. So if I do like a dotted line down there, you know, I can start saying, well, can I work out the area of that triangle there? And then I might want to work out that length just there so that I've got a base and a height, and then I can find the area of the triangle. So drawing on these extra lines is starting to help give me some insights. But I really want to know what that point of intersection is just there. And I could work it out by counting squares, but I might like to think of some other geometrical ways of doing it. So what I'm going to do is I'm going to show you what we've done with this problem on the Enrich website. So if
Alison,
I go, yep.
Can I just mention something? In the two examples we've done so far, we started from particulars and gone to the general. We started with polygon rings with pentagons, and then looked at hexagons and octagons, heptagons. And I mean, we didn't mention it, but it's surprising that everything we tried made a ring. And it does seem to suggest that perhaps whatever polygon we start with, we're going to be able to make a ring with. But there is that possibility of generalizing. With cyclic quadrilaterals, we started with the 9 dots and encouraged children to go to 10, 12, 15, and then generalize. Here, you're doing exactly the opposite. You're starting with this image, which is very general, with no dimensions, and suggesting to students that one strategy that mathematicians use when they are stuck is to go to the particular. John Mason talks about this all the time. So
yeah, try a special case, yes.
Try a special case. And your idea of maybe drawing a 6x6 square and drawing this, when we were talking this morning, we were talking about, well, 6x6, 12x12, possibly 9x9 were easy numbers to try. But I like this idea that we move from the particular to the general, but sometimes we have to move from the general to the particular.
Yeah, and that's one place where there's an advantage as a teacher if you've looked ahead and looked at the solution of the problem, because some squares yield the solution to this problem more easily than others because of the proportions that are involved. So Charlie's just mentioned doing a 6x6 square or a 12x12 square. Because of the proportions that you get when you start drawing on this, that's going to give you intersections of lines on grid lines. So what we've done with the problem on Enrich, and you can see that this is a key stage 4 problem, and we've given it a challenge level of 2 stars, which means it's got some chunky problem solving in it. It's not immediately straightforward for every student. But in order to offer a little bit of scaffolding, once students have had a go at the problem, we invite them to think of 3 different proof methods. And this is a proof sorter activity. So the steps of the proof are in a muddled up order, and it's a sense making activity. Can you look at somebody else's proof with the steps in the wrong order and then put those steps in the right order? So the 3 methods suggested in this case, there's a coordinate method, which is very similar to the idea of drawing it on a square grid and then working out where these intersections are using coordinate geometry. And then there's a similar figures method. And in that, it relies on noticing that triangle, in this diagram, triangle AME and triangle ECD are actually going to be similar triangles. And because you know that AM is half of DC, then that allows you to deduce that this point E is 1/3 of the way down the whole square. And that's the key to being able to crack it and to start putting some dimensions on this diagram to start working out areas. And then the third method that's in the proof sorter is using Pythagoras to start working out some of the lengths in there. And so, you know, you might not use all three of these. It might be that you've got a class and you've been doing some work on similar shapes, and so you want them to think about it in terms of this. Or you might have recently been doing straight line graphs and intersections, and you want to show them how that can be useful in a coordinate geometry way. So you might use this method, or you might have students who've recently been working on Pythagoras and use this method. So we're not going to go through the proofs for these, but they are all there for you to have a go at after today. Or you might be able to find a different way to prove it for yourself as well. I will draw your attention though, as well as having teachers' resources on the problem, you also have the opportunity to look at student solutions to the problem. So you can see how the different proofs figure themselves out and what the answer is. And we know that teachers don't have time to work through every problem for themselves, even if you would very much like to. So a helpful shortcut, rather than having to figure out every way of doing every problem for yourself, is to have a look at the solutions to see how other people have done it. So the journey we've taken so far then, we've talked about giving students a framework for understanding a proof in cyclic quadrilaterals. So doing the examples numerically and then that giving insight into the general proof. And then here, taking things a little bit further with geometrical proof to modeling what a geometrical proof looks like and what the language might be that is used in proof. So by doing those two problems, your Key Stage 4 students would be well prepared for some of the hardest geometrical reasoning that is on the GCSE spec. I really want, in the last problem that we're going to look at, I want to go back to the idea of geometry sometimes giving you things that will surprise you. And so what we're going to do for this is, Charlie, I'm going to pose the problem to you, and I'd like you to have a go at it under the visualizer for everybody to see what you're doing. And I'm kind of going to narrate what it is that you're doing, but then hopefully there will be an element of surprise. And then from that, we can think about where this links in with the idea of proof. So if you've got some dotty paper, yeah, oh, brilliant. You've already got it there with a set of coordinate axes. And what I want you to do is I want you to draw a quadrilateral, and I think I want it to be a convex quadrilateral to start off with. So why not pick sort of something bottom left, top right, bottom right, but sort of anywhere within that quadrant. It doesn't have to be a square or a rectangle. It can be a nice irregular quadrilateral. So Charlie's going to choose 4 points, and he's just going to mark the coordinates of the 4 points that he chooses. So you've got 1, 1.
Thank you. Okay, so I'll go for a point around here.
So that's 11, 2.
Something around here. Okay, is this clear enough?
Yeah, that's perfect.
Okay.
Okay, and I'd like you to join your 4 points to make a quadrilateral. And so if I was doing this in the classroom, everybody would be drawing a slightly different quadrilateral. It's very unlikely that they would draw exactly the same thing as their neighbor. So we're generating a whole landscape of examples straight away. And so we're starting to see whether there are any general results emerging from what people are doing. And just because I know not everyone will have squared paper to hand, but people might want to have a play for themselves, I'm just going to post a link in the chat now, which is to a GeoGebra interactive that does just the same as what Charlie's done on screen. So you can move 4 points about and it will tell you the coordinates of your 4 points. Okay, Charlie, your next task then is to work out the midpoints of your 4 line segments that you've got there. And anyone playing along with GeoGebra is going to find this much easier because they can just make your example on the screen and then just click the Show Midpoints button.
So between 1, 1 and 3, 6, the x coordinates are up to 4, so the average is 2, and the y coordinates are up to 7, so the y coordinate, the average is 3.5. I've got 1 out of 11, then up to 12, so the average is 6. So the coordinates will be 6 and 1.5. Here we've got a 9 and 11, so the average is going to be 10. And the y coordinates are 2 and 8. The average of those is 5. And over here, 3 and 9, add up to 12, average is 6, 6 and 8, average is 7. Okay?
Okay, and then what I'd like you to do is I'd like you to join the 4 midpoints to create a new quadrilateral in the middle of your original quadrilateral.
Okay.
And this is the moment for the element of surprise again, because it looks very much like, even though you started with something that was quite irregular, it looks like you've ended up with a parallelogram. And if anyone who's clicked on the link to go to the GeoGebra version of this, no matter how you move the points around, it seems as though wherever you put those points, you're always getting a parallelogram in the middle.
Let's check, Alison.
I was going to say, with the coordinates, I think we can check quite easily if it looks like a parallelogram or if it actually is. So how would you go about proving that this is a parallelogram and not just a near miss?
So this line here and that line there. So to go from that point to that point, I go 4 across and 2 down. And from this point to this point, 2 till 6, 4 across, 3.5 to 1.5 and 2 down. So these 2 lines are indeed both parallel and the same length, because both of them involve going 4 across and 2 down. And so what about these 2 lines here? I go from 2 to 6, so 4 across, 3.5 to 7. So it's 4 across, 3.5 up. And from here, from 6 to 10, that's also 4 across, 1.5 to 5, that's also 3.5 up. So these two lines are parallel and I've got to say, so the opposite sides are parallel and have the same length. So at least this one is a parallelogram.
Okay, and so I'm just imagining this being replicated all around the classroom. And so in terms of the mathematical skills that we're practicing here, we're practicing some coordinate geometry because they have to work out the points to begin with. Finding the midpoint of a line segment is, you know, nailed on GCSE topic that gets asked time and time again. So they've got to find the coordinates of the midpoints. And then in working out whether the lines are parallel, effectively what they're thinking about is they're thinking about the gradients of the line. So you didn't actually work out the gradient, you just worked out the x and the y distance, but you could go one step further and say that the gradients of the line are the same by doing the division. And you could even work out the exact lengths of the line and bring in some Pythagoras there. So just from this one starting point, we're ticking off loads of the bits of geometrical reasoning that we know that our students need to do. But if every student in the class has come up with a parallelogram at the end of this process, then that suggests that we need to go back to thinking about proof again. We want our students to be skeptical and to say, well, it might just be chance. It's quite unlikely that we would all pick something that leads to a parallelogram, but how do we know for sure it's always going to be a parallelogram? And so I want to talk a little bit about how you might use coordinates for this. And so what I'm going to do is I'm just going to share my screen and show the GeoGebra version of it. So this is exactly the same as Charlie's diagram just there. And I can turn the midpoints on and off to show the parallelogram. So instead of having 1, 1, 3, 6, 9, 8, and 11, 2, I could start specifying these coordinates as general things. It doesn't make any difference to move one of the coordinates to the origin. And again, that's a nice conversation to have with students, that if I'm trying to draw a general diagram, one of the points being fixed at 0, 0 can often make the algebra easier in my proof, but it doesn't actually make any difference. It's just a coordinate transformation. So I can pick my points, and instead of having them labeled with numbers, I could start labeling them using letters. So I might say that that's 0, 0, that point is AB, that point is CD, and that point is EF. And then I can calculate the midpoints in terms of A, B, C, D, and E, and F. And then I can start working out about these lines joining the midpoints and do exactly what Charlie did with the specific case using numbers. I can start working out in the general case using algebra. Another option that I can have then is, instead of using the coordinate labeling, I can actually use vectors for this. So I can say, let's let this one have position vector A, and then this point can have position vector B, and then this point have position vector C, and then I can work out the midpoint. I can work out this vector and this vector in terms of A, B, and C, and then I can work out the midpoints in terms of vectors, and then I can use what I know about parallel vectors to show that this vector and this vector are in fact the same vector. So vectors is one of those topics that students are often a little bit resistant to when it's first introduced, but there are certain coordinate geometry problems like this where using vectors makes it fall out really quite nicely. Just to prove that, I did do this with vectors earlier on, and I'm just going to hold up to my webcam. It was that much working to do it with vectors, so it was.
Can you hold it a bit closer, Alison?
No. because then you'll see how tatty my written work is, and I really don't want to do that. But yeah, it was less than half a page of work, start to finish, for the proof. However, if we look at this problem on Enrich, there's another version of the interactivity here. And this is going back to that idea again, that you think about a problem differently if you're thinking about it on squared paper as opposed to plain paper. So you can do exactly the same task, but instead of having it on a coordinate grid, now A, B, C, and D are just 4 completely free points on the grid. And I can show the midpoints P, Q, R, and S like that. But it's also given me an opportunity to take this one step further, which is to show the areas. So the total area of my original parallelogram and of my original quadrilateral, and the area of my parallelogram in the middle. So there's an extra problem there to consider and extra conjectures to be made. And so how would you go about proving it without the scaffold of coordinate geometry? Well, what you can do is you can do that trick again of drawing an extra line. So I'm going to draw the diagonal AC just as a dotted line like that. And that's supposed to be a straight line. So just put in the chat, what do you notice now that I've put the diagonal AC onto the grid, onto the shape? So Josh says that it looks like it's parallel to the lines QR and PS. Now you've said it is parallel. I've paraphrased a bit and said it looks like it's parallel, because I think we would need to be able to convince ourselves of that. How can I convince myself that this line and this line and this line are all parallel? Any suggestions? I'm going to add one extra thing that I know, because I know that S is the midpoint of DC. So I know that that line and that line are the same. And I know that that line and that line are the same length. And yeah, I can do something clever thinking about angles. I need to be careful not to use the fact that I think it's parallel to prove it, but I can actually use triangle PDS and triangle ADC. I know that this angle here is common to both of those triangles, and I know that because this length is double this one and this one is double this one, that I've got 2 similar triangles. So ADC is an enlargement of PDS, an enlargement from the center of enlargement D. And so as soon as I know that they're similar triangles, I know that that angle and that angle are the same, and then that that angle and that angle are the same. And so then that is showing me that I've got some corresponding angles. So I've got parallel lines, and I can use exactly the same argument with triangle ABC and QBR, that they are similar triangles. And so then that tells me that this line is parallel to this. It's actually an application of something called the triangle midpoint theorem, which is that if you join the 2 midpoints of a triangle, the line that you get is parallel to the base of the triangle, and it is in fact half the length of the base of the triangle. And you get that as well from the similar triangles, because if this is half of this and this is half of this, then this length here must be half the diagonal. And that's the key to the thinking that you need to finish this problem off and start thinking about area. Now, I'm conscious that we're coming to the end of our time, so I think I'm going to do a little bit of summarizing of some of the ideas that we've shared today, and then Charlie's going to just show you how to find a couple of things on the Enrich site. And so, yeah, in summary, some of the big ideas when thinking about geometry is making sure that we're scaffolding some of the more complex proof stuff by showing numerical examples first of all, thinking carefully about our choices of when to do geometry on plain paper and when to do it on squared paper, because whether you use a coordinate system or not, gives you a very different view of how to solve a geometrical problem. And we want students to be fluent in both. We want them to be able to do things with and without coordinate geometry methods, but also the wonderful element of surprise that's popped up in a couple of these problems. So Polygon Rings, you have this wonderful moment of surprise when even with these horrible shapes that don't normally do anything nice, fit together to make a ring. And the element of surprise in the last problem we just looked at, quad in quad, where no matter what quadrilateral you start from, as soon as you join the midpoints, you have to end up with a parallelogram. There's no other option but getting the parallelogram there. And so in the same way that Charlie and I get very excited with number problems sometimes, and being able to prove general results and do these very exciting things and have number tricks that lead to an exciting outcome, and being able to say, I know your answer is a multiple of 9. These are the geometrical equivalents of that. I know you've ended up with a parallelogram. No matter what you start with, it's almost like magic. But then when you can start to do the geometrical reasoning, it's not magic at all, it's mathematics. So Charlie, I'm going to hand over to you so that you can show us where to find the things that we've done today. And then unfortunately, that'll be game over.
Thank you, Alison. Just to reassure everybody, at the end of this session, we'll send an email out, well, we'll send it to Vicky or Jane, whoever's been communicating with you, with links to all the problems that we've referred to today. And I think I might also add a link to a lesson that Alison and I taught, which led to a group of students who we'd never worked with before, discovering Pythagoras' theorem. And it mirrors how we would imagine working on cyclic quadrilaterals with a group of students, starting from very particular cases and building up to the generality by getting students to work on different tilted squares, sharing their findings, and slowly, and every time they shared, to encouraging them to notice, to talk about what they noticed, notice the pattern, start conjecturing, and slowly developing, working towards a generalization, which then ended up in a proof. So that journey of a problem that we haven't talked about today, but the video might give you a taste of how we imagine working on these problems, whether it's polygon rings or quad in quad, but also likewise thinking about kite in a square, the idea of starting with a general problem and then getting students to work on very particular ones where they could draw on square paper or dotted paper, like Alison said, and again, share their findings about what fraction of their kite made up the whole square, conjecturing that it always was 1 over n, and we're not going to tell you what that n is, just in case you want to work on it, and then working towards the general case, and having that proof sorting activity, so that we introduce them to sort of rigorous proof that will be necessary if they carry on studying. So don't worry, we will, an email will come your way either tomorrow or by the end of the week, I imagine. PTI are always very efficient about these things, with all the links. So the last thing I want to do is to share my screen and show you, so a general page on the, so if you go to the Enrich homepage, you'll see that there is a link to the secondary teachers page, or lozenge there, the secondary teachers page. And what we've done is organize resources for secondary students, secondary teachers. And one of the things that we did was set up a page here called What We Think and Why We Think It, where Alison and I shared some of the thinking that went into producing our resources and links to some articles that have informed our thinking. So we'll put a link to that, some short articles and some longer ones, and 2 or 3 books as well. if I go back to secondary teachers page and go to the secondary, we've also got collection of resources on enriching the secondary curriculum, and actually our tilted squares lesson is there. And the last thing I want to show you is that we've also got a curriculum mapping document. I'm not going to click it on now because it takes a few seconds to download. So I've already clicked on it earlier, and I can just show it to you. And this is what it looks like. And we've got resources on number, on algebra, on geometry. I've got the geometry tab already open. And let me just move this out of the way. And you can see here that we've got some problems on angles, polygons, and geometric proof, which is what we've been focusing on today. And you'll see that we've got among these all 4 problems that we've talked about. So Polygon Rings appears here in what could be a year 8 column. We've got Cyclic Quadrilaterals, and I think Cyclic Quadrilaterals appears perhaps in 2 places. It appears here in a year 9 column, but I think we also had it in a year 10 or 11 column. I'm not sure I can find it right now. Oh, no, I can't find it. It may appear further down. And what else did we do? We did kite in a square.
And quad in quads there as well, yeah.
And quad in a quad. Okay, so I got to that page by clicking on the secondary curriculum mapping document. There are many more problems like that, which require students to think mathematically while still addressing the topics in the curriculum. And we have focused today mainly on angles, a bit on area, but we've definitely focused on topics that students are going to be encountering in the curriculum, but which require justification, proof, conjecturing, generalizing, and the like, which was the task we'd set ourselves today. So if you've been with us for the other webinars, when we did some work on handling data and on number, you'll know that we're very keen to offer students the opportunity of encountering the topics in the curriculum while at the same time thinking mathematically. And the problems in the curriculum mapping document will do that.